All right, folks, welcome to our review session for the final, spring 21. We've got our first question about heat to mass type of problem. This would have come up in chapter 5, talking about conversions between, say, the enthalpy or heat and a given amount of mass. So in this problem, for instance, the wording says, given this initial amount of oxygen, how much heat, and again, that heat is related to delta H. Delta H and Q are tied together. This is that concept for heat. But how much heat is released when we're combusting in excess benzene? So ultimately, what we want to do is set up a conversion, a calculation that enables us to connect the oxygen from the balanced chemical reaction. And I will say that before we started recording, we took a moment to make sure the reaction was balanced. This is where the coefficients came from. But we're trying to set up a ratio between the oxygen and the enthalpy, the heat. So the first step in this process is going to be converting from grams to moles. And then we're going to create a ratio between moles and the enthalpy, and then use the ratio to finish the problem. That's how I think about the 3 steps in this example problem. So that first step, converting grams to moles, you've got O2 in the problem, so we're going to need the molecular weight of O2. Take a second and calculate that. Should be twice the value for oxygen, which is 15 and a bunch of 9s and maybe a 4. So what is that? 39.9988. Can I get some corroboration, text or voice chat? Is this the value you all get? 39. Whoa, excuse me, 31?
I got 31.9988.
All right, good. Thank you. Grams per mole. And remember that the molecular weight is always defined as grams per 1 mole. It doesn't matter what coefficient I have in the equation, the molecular weight is always defined grams per 1 mole. So let's do step 1. Step 1 involves converting from grams to moles. So we're going to start with 15.2 grams of O2 and set up our little train tracks. If I'm in grams and I want to go to moles, I'm going to divide by the molar mass. So in this case, I've got 31.9988 grams of O2. And this is where I'm saying again that it's always defined with respect to 1 mole when we're thinking of the molecular weight. So this process right here is step 1 from above. Let me expand my screen a little bit here. There we go. All right, so we can get a number for that, or we can continue setting up the train tracks. In order to do the next conversion, we're going to need to think about the units that are available. And right now, that's moles of O2. And so to convert between moles of O2 and the heat, we need a mole to heat ratio. And this step is the step where we need the coefficient from the balanced chemical equation. So in this case, we're writing 15 moles of O2 is proportional to that negative 5.84 times 10 to the 3rd kilojoules. Right, that was all given at the start. Just like we made mole to mole ratios in the past, now we're making a mole to heat ratio. So to use that, the final step here is to plug the ratio in to my train tracks. In this case, I've got moles on the top, so I'm going to put moles on the bottom. 15 moles of O2, and then on the top, the heat value, negative 5.84 times 10 to the 3 kilojoules. And at this point now, I can cancel moles of O2, and I'm left in kilojoules. I should have said that at the beginning, by the way, trying to calculate the heat in kilojoules. Now that we've got our unit into kilojoules, we just need to multiply everything together on the top and then divide by everything on the bottom. So take a moment now and try to crunch those numbers and throw your vote in the chat. I'm going to pause recording while we work these numbers out. All right, now that we've come to an agreement about the number, the value seems to be minus 184.94, and that's enough sig figs for now, kilojoules. And we can now go back and think about the number of sig figs. We started with 3 sig figs, so it looks like we're going to be limited to 3 sig figs as well. Sorry, I should say that the enthalpy also had 3 sig figs. I do want to make one more point that the coefficients do not count towards your sig figs. So the fact that that has 2 sig figs is not important here. The coefficients are exact quantities and they don't impact the sig fig determination. In this case, it's the enthalpy or the mass that determined how many sig figs we would keep. Since they were both 3 and we're doing multiplication, I'm going to be keeping 3 significant digits. In this case, the final answer then, minus 185 kilojoules, round up, no exception. And that's the final value in this case. All right, we had another question about chapter 19 material this time, closely related to some chapter 5 material about Hess's law. But in this example, we've got a given chemical reaction, and we're trying to use the information in this table to calculate the Gibbs free energy. And in this case, the key equation that you've got to remember is that delta G of the reaction is delta H minus T times delta S. So this is the setup that we have to use. And that means we've got to do kind of 2 steps. One related to the enthalpy and one related to the entropy. And this is ultimately where that concept of the total for the products minus the total for the reactants comes back into play. And again, that was originally from chapter 5 material about Hess's law. So the first step is to calculate delta H. And to do that, we're going to have to do delta H of the products minus delta H of the reactants. And I'm writing it out here fully with the word so that you can see it. But I've used another symbol for this thing in the past, right? RXTS. Just for short. It's got less letters. That's why I like it. All right, but this is the process. So we've got to calculate this quantity and then follow it with a calculation for this quantity, stitch them together in order to get the enthalpy. Then we're going to do exactly the same thing for the entropy. So let's get it done for delta H first. So for the products, we've got to take the stoichiometric coefficients and line it up with the quantity in our table. But I actually just marked the incorrect one. Remember that the states of matter are important, and so we need the liquid value. So in this case, I need 2 moles of H2O times the negative 285.8 kilojoules per mole from the table. And that's my only product. I don't have any other products. So this is going to be the only thing I need to calculate here. Let's take a moment and get a number for this. Throw it in the chat whenever you're ready. It's going to be negative. A 5. After that, I'm not so sure. 7. That seems pretty good to me. Got corroboration? Excellent. And now also notice that the units are kilojoules. So we've got delta H of the products. Now we go to delta H of the reactants. In this case, my two reactants are hydrogen and oxygen as gases. Throw it in the chat. What is the value of delta HF for both of these elements in their elemental forms? Yeah, I got to vote for 0, and that is correct. Because both of these elements are in their elemental form, the enthalpy of formation is identically 0. So the delta H of the reactants is equal to 0 for this example. Do not assume that this is general. Let me say it one more time. For this specific example, we found delta H of the reactants is equal to 0. This is not general, and more generally, this number will be non-zero for the reactants. It just happens to be 0 for this example. So with that in mind, we calculate delta H of the reaction, Rxn, notice, as negative 5716. Sorry, there's a decimal there. Minus 0 kilojoules for the reactants to just get back minus 571.6 kilojoules. Ooh, a lot of work, but the faster you can do this, the easier your life will be, right? The more quickly you get this process down, the more time you'll have to work on other problems. And it's really not bad once you're used to it. You know, we're taking a lot of time right now, but you can do it much faster after you've practiced. This is one piece of the puzzle though, folks. We've got to calculate an entire other puzzle piece before we can even calculate delta G. Let me pause here and check for questions. All right, and we're back for part 2 of this problem. In the next phase, we need to calculate the information about delta S of the reaction, but we're using the exact same process. Remember that delta S of the reaction is S of the products minus S of the reactants. But in this case, nothing is equal to 0. At finite temperature, right? At standard temperature, that's what that little circle on the top means. The entropies are non-zero. And that's because entropy is defined to be 0 only at 0 Kelvin. Just a conceptual point I wanted to make clear one more time. So let's go through the process one more time to calculate delta S of the products. We're going to be using that 2 moles that we had the first time, and then we're going to match it up with the value from the table for the entropy this time. And just like before, Moles cancels out, and I'm left in kilojoules. I don't have any other products, so in this case, we just need to multiply them together again in order to get a value. So let's get a value for this delta S of the products. And I'm sorry, this should just be an S. It's really a technical detail, folks, about why it's a delta or not, and I'm not concerned if you use a delta in your writings, but to be technically correct, it would just be an S. Again, not a big deal. All right, I've got a vote for 139 and change, and I also agree with that. 139.8 kil. Oh, I'm so sorry, folks. I've messed up the units. I'm so glad that we caught this down. Rewind. Looking at the table, our units for the entropy are different than the units for the enthalpy. And a moment ago, I didn't catch that. So let's backtrack just a step. The units for entropy are joules on top, moles on the bottom, and Kelvin, right? That's a capital K. I'm just going to write out Kelvin so that you see it here and we're clear about what that means. So entropy is energy per temperature. That's the way I would think about it. In this case, we're multiplying by moles, so the moles drops out. But then the final value is going to be joules per Kelvin. Right? So delta S of the products is 139.81 joules per Kelvin. And this is important when we come back to calculate delta G, because ultimately we're trying to get back to this equation in kilojoules. All right, so now we've got S of the products done. We can do S of the reactants, the more interesting one. I've got two different coefficients now and two different values to add together. So in this case, we're going to have 2 moles of H2 times 130.6 joules per mole Kelvin. And we're going to have to add to that another term coming from the oxygen, 1 mole of O2. And now the value in the table is 205.0 joules per mole Kelvin. So if you're looking carefully again, moles cancels out. I'm left in joules per Kelvin, and we can add these together to get the reactants value. So let's do that. What do we get? S naught of the reactants. Two times 130.6 plus 1 times 205.0. Yes, votes coming in now. I also get this value, 466.2. And keep in mind, again, the units are joules per Kelvin. Ooh, long problem. We're 2/3 of the way done. The next phase involves putting these two things together. So I'm going to pause here. All right, to finish up this problem, we have to combine our knowledge of the entropy for the reactants and the products, and then we'll be able to wrap up our delta G. So delta S in this case, for the reaction, we've got products 139.81 joules per Kelvin, subtracting off the reactants 466.2 joules per Kelvin. And we're going to get a negative value now, a negative value for delta S. 139.81 minus 466 and change. I get minus 326.39 joules per Kelvin. All right, That's some good information. If we're thinking about sig figs, in this case, yeah, it's a little subtle. To be ultimately technically correct, we would only have 3 sig figs here because this is a multiplication problem. So that would lead us to having the ones place as the least significant decimal place. And the reason I say that is because the last step for delta S is a subtraction. And so we have to go by the least significant decimal place. And in that case, it's going to be the ones from this 139. Like I said, though, a bit subtle. With this piece of information, though, we can finally calculate delta G. Woohoo! I'm going to pause while we set up the next slide, and then we'll finish the calculation. All right, so to finish the problem, we're going to need to combine information about delta H, S, and the temperature, T. So in this case, one of the hangups, folks, is what to do with the temperature. Keep in mind that the units of entropy are per Kelvin, and if you're given something in degrees Celsius, we'll need to convert. So in this case, 273.15, we add that to our 75 degrees Celsius, and we're going to get the temperature in Kelvin. So 75 plus 273.15, and do always use the 0.15 on the exam. That is the officially correct conversion. 348.15 Kelvin. If we were looking at sig figs, we would be looking at the ones place. So keep in mind that the temperature has 3 sig figs. That's what we can take away from this analysis. So we're ready to use the equation. Delta G is equal to delta H minus T times delta S, except there's one catch. We have to convert to kilojoules. And so the simplest, and the reason I say that, 1, because the question asked for it, and 2, because delta H is also in kilojoules. So in this case, to do that conversion, we have to multiply by 10 to the minus 3. However you want to do that is fine. One way to do that would be to move this decimal point 3 places to the left. That would give me negative 0.3264 kilojoules per Kelvin. And now that I know what this value is in kilojoules, I can bring it down to my equation for delta G. So let's put these numbers together and finally get a value. Negative 571.6 kilojoules from delta H minus the temperature in Kelvin, 348.15 Kelvin, multiplied by the value kilojoules per Kelvin, negative 0.3264 kilojoules per Kelvin. Kelvin over Kelvin drops out, and we can finally get a value. What I would recommend is to calculate this number first, and then we can do the subtraction problem. So what do you get for that number? 348 and change times 0.3264. And I get a negative number, negative 113.63616. 3 sig figs, because we've got 2 things with 3 sig figs being multiplied together. If we're looking at the final step, we're going to be rounding at the ones place. But let's get a number here. What is the final value of delta G here? Throw it in the chat whenever you're ready. I see a vote there. Thank you, Blair. I'm getting a number that's very close to that, and then with the rounding, it becomes minus 458. So let's walk through that last step. Minus 457.96 kilojoules, and we can round to finally 3 sig figs minus 458 kilojoules. A long problem, but if you can get the process down, you can do it very rapidly. I'm going to pause the recording, and then we can take some more questions about this or anything else. Our next question was about chapter 5 material, looking at heat, work, and internal energy or energy. Sometimes it's stated one way or with both words there. But in this particular problem, the setup of the problem described a process where there was a net loss in total energy, and the system absorbed a certain amount of heat. Ultimately, your task is to calculate how much work is involved in this process. But the vocab is a little kind of mystery that you need to unravel in order to know the sign of each of these quantities. So let's start out with the equations that we need. The first one that we need is that the total change in energy is going to be the sum of heat plus work. And ultimately, this work is the thing we're trying to solve for. So you want to solve for W. So the last equation that we're going to need to like wrap up the problem is W equals delta E minus Q. Right? That's the final equation we need. But before we get there, we need to figure out what's going inside of this equation for delta E and for Q. And this is where the vocab from the setup of the problem is important. If the system has experienced a net loss in energy, then delta E is negative. So in this case, the sign of my thermodynamic quantity is negative. The value is 4.8 and the unit is kilojoules. Remember, 3 things are needed to specify a thermodynamic quantity. That's one part of the puzzle. The other part is the heat. And in this case, we're absorbing, right? Absorbing heat. And absorbing is another synonym for gain, right? To gain heat. And in this case, when we're gaining heat, an endothermic process, then the sign of the heat is positive. 13, wow, I messed up. Was it just 13 kilojoules?
Yes.
Okay, great, 13 kilojoules. There it is. So we've got a positive, we've got a magnitude and a unit now. And with both of these pieces, now we can run over to that final equation and get a value for W. So let's plug in the two values. We've got minus 4.8 kilojoules. And keep in mind that the decimal places are what matters for subtraction. Then we're subtracting 13 kilojoules, which has the ones place as its least significant decimal. So we're going to get a number that's more negative. In this case, I think W is minus 17.8 kilojoules. But we're going to have to round at that first ones place. So I think the final value should be negative 18 kilojoules. So the next question was asked about the Hess's Law type puzzle piece problems where you're given a set of reaction and expected to calculate the final reaction for some other scheme. In this case, we have two puzzle pieces. We need to put these puzzle pieces together in order to calculate the total reaction on the bottom. So let's take a look at the different puzzle pieces themselves. First of all, we've got NO on the left-hand side, the reactants side. And so if I'm looking at my two puzzle pieces, I'm probably going to need to flip both of these so that I can get NO on the left-hand side. So that first reaction we're going to have 2NO going to N2 gas, O2 gas. And the second reaction, we're going to have NO gas plus 1/2 oxygen goes to NO2 as a gas. And because both of these have been flipped, then we're going to need to flip the delta H's. So in this case, negative 202 kilojoules. And this one, negative 97 kilojoules. I think that's correct. Any questions so far? Then the next step will be to scale some things in order to get the coefficients to line up. So in this case, we've got a 2 here. I'm sorry, a 1 there, a 2 up top, and we're trying to get to 4. And so I think that means we're going to need to multiply this second reaction by 2 to get 2NO as a gas plus O2 as a gas, going to 2NO2 as a gas. And we do want that 2 because that's in our answer as well. So we should be on the right path here. I'm sorry, this is for B. We've got to multiply that by 2 as well. This should be 194. And then we can set up the addition problem where we add these two reactions together. So in this case, I've got 2NO as a gas plus, nope, sorry, a reaction arrow, N2 plus O2. The oxygens are on two different sides of the arrow. So when we add these species, add these equations together, the oxygens are going to cancel and we'll be left with the target reaction. In this case, 2 plus 2 is 4. And this will produce 2NO2 plus N2. And now we need to add these things together. Delta HA plus delta HB, negative 396. I believe this is the correct answer. I'm going to go ahead and stop recording and then we can open up for some more questions. All right, the next question is about going backwards. If I'm given a delta H, how can I calculate the amount of grams? In this case, the process is the mirror or the backwards version of our first example. So our first step is going to be making this mole to heat ratio. And then we're going to use the ratio to calculate moles. And then the final step will be to convert from moles to grams using the molecular weight. So these are the three steps for this problem. So that first one involves coming up with the mole to heat proportion or ratio that we need to start. We're given that delta H for the reaction is minus 588.4 times 10 to the 3 kilojoules, for example. And that's going to be proportional to 2 moles of benzene, since the question is asking us about C6H6. So the first piece of information that we have by all the stuff that's been given is that 2 moles of benzene is proportional to negative 5.884 times 10 to the 3 kilojoules. Now we're going to use that ratio, combine it with the amount of heat given on this process, and that will tell us how many moles of C6H6 have been consumed. So we start out with negative 2.56 times 10 to the 2 kilojoules. And we snap this ratio in place. In this case, we've got minus 5.884 times 10 to the 3 kilojoules on the bottom, and 2 moles of C6H6 up top. Kilojoules will cancel from this particular ratio, and I'm left in moles. To convert from moles to grams, I need the molecular weight. So we probably should have started with that calculation. But let's take a second and get this value. It's 12 by 6 plus 6, 72-ish, 70. What do we got? Just guessing at this point. 78 and change. Throw it in the chat whenever you're ready. Just got to grab the numbers from the table. Yep, I get that value or something close to it. I got 78.1. Did I make a mistake? Need some corroboration from someone else. What value do you get for C6H6? I got this value, so I'm going to assume we're there. Using this value now, we can snap it into place in order to convert from moles to grams. In this case, we're going to be multiplying. We've got 1 mole on the bottom and the molecular weight up top. So there was a 4 here. Moles will cancel, and I'm left in grams, which is exactly what the question wants. So now we need to multiply everything in the top and divide by everything in the bottom. I'll pause the recording while we work out the final value. All right, we're back with the final value, 3.398 and change. In this case, we get 3 sig figs from the original value. And so our final value is going to be 3.40 grams of C6H6. So one more time to recap the process. We were given an amount of kilojoules. So our first step was to create the ratio between kilojoules and moles. In this case, we need the balanced chemical reaction in order to do that. We had 2 moles proportional to this amount of heat, which we then used to convert the given amount of heat into moles of benzene, C6H6. Once we were in moles, we multiplied by the molar mass in order to cancel moles, leaving us in grams, which is what the question was ultimately asking for. Sig figs got us down to 3.40 grams. Our next question takes us way back when, to chapter 6 material, test 2, concerning the energy and frequency of photons. Do keep in mind that the values of H and C will be given to you. You do not need to memorize these, but I'll just go ahead and write them here so that we have them for referencing. I will provide the values on the As You Learn page, as I have done in the past for previous tests. But you've got to know how to use those values. And in this case, we have this equation E equals H nu. So when people ask you what's nu, you can tell them E over H, because that's what you get when you solve for the frequency. So ultimately, this equation here, right, when I solve it for this Greek symbol nu, I get E divided by H. At this point, we need to make sure that our stuff's in the same units. In this case, everything is in joules, so we're okay. We don't need to do any extra conversions. So on the top, I'm going to write 3.59 times 10 to the minus 19 joules. And the value of Planck's constant on the bottom. And this is joules times seconds, folks. Energy times time. The joules over joules cancels out, leaves me in 1 over seconds, which is what I should have for a frequency, right? Hertz, 1 over second. So take a second, calculate the ratio of these two things. What is 3.59 times 10 to the minus 19 divided by Planck's constant? Should get a large number. Throw it in the chat. It's got a, yeah, it's big. I've seen bigger numbers. A mole is bigger. But in this case, we're going to get a number 5 and a little more times 10 to the something. So what are y'all getting? Throw it in the chat for me. Okay, yep, this looks like about the right number to me. 5.418 should be enough sig figs. Why do I say that? Because we're going to be limited to 3 sig figs based on our initial number. Well, shoot, just the right amount. There we go. Times 10 to the positive 14, 1 over seconds. And remember that 1 over seconds is a hertz. These are the same thing. This guy Hertz did a lot of stuff with sound back in the day. So he gets his own unit. But there we go. Now we can round. We're going to end up at 5.42 times 10 to the positive 14 hertz. And that is an example of going from going from the energy and figuring out the frequency. Our next question is about a titration problem, looking at, say, how to find the concentration of something. In this example, we're going to find the concentration of base, but the process works for either one. The crucial thing is the equivalence point, which says that my moles of acid are equal to my moles of base. Right? The equivalence point is where that's true. And because of that, the equivalence point allows me to set up a relationship, a ratio between moles of acid and moles of base. So at some point in this problem, we're going to need to use the mole to mole ratio between the acid and the base in order to solve this problem. So the first step is going to be using the information given to try to calculate something about this problem. And ultimately, we're going to be using equations like M times V, right? Concentration times volume in order to get moles. Because ultimately, again, this equation says moles equals moles. So let's start out with the acid by trying to find out how many moles of acid we've added. In this case, the moles of acid is the concentration 6.5 moles HNO3 in 1 liter times a volume, which also has to be in liters. And that's another subtle point here, folks. So the volume of acid is given in milliliters, but we have to convert that over into liters by dividing by 1,000. So in this case, we're going to be multiplying by 0.0352. We've converted milliliters into liters. And the only reason I'm doing this stepwise is so that you actually see each of the steps. If you just memorize a process, then you won't understand necessarily that this condition is moles equals moles. You might just assume that it's the same as dilution, which is not necessarily true. So in this case, let's get a value. 6.5 times 0.0352, 0.2288 moles of HNO3. Now we're going to use the mole to mole ratio to convert acid to base. So in this case, I've got 2 moles of my acid proportional to 1 mole of my base. And why are we equating these things again? Let me just restate one more time that the equivalence point allows us to make the connection between moles of acid and moles of base. So we're going to use this value, we're going to use this conversion factor, and then we're going to have moles of base at the end of this calculation, this step in the calculation. 0.2288 moles HNO3 times 2 moles on the bottom HNO3, 1 mole on the top. So what is this? 0.1144 moles calcium hydroxide. Moles of HNO3 drops out, and I'll be left in moles of calcium hydroxide. The final step in this problem is combining the moles of calcium hydroxide with the volume from calcium hydroxide. And to calculate a concentration, we have to do division, moles divided by liters. So on the next slide, in order to calculate the concentration of calcium hydroxide, we're going to need to do that division between the number of moles, which is 0.1144. And I'll advance the slide in one moment. And we're dividing that by the volume in liters. So in this case, we were given 22.7 milliliters. But we have to convert to liters. in order to calculate molarity, big old capital M. Capital M has to be moles divided by liters. So now in this case, you can run that through your calculator. We're going to be limited by the 3 sig figs here. So let's see what we get. 0.1144 divided by 0.0227. 5.0396. And rounding here, big old capital M. The concentration of calcium hydroxide is 5.04 molar. And that's how you would tackle these titration type problems. We found a mistake in this earlier calculation. There was a factor of 2 missing from the original numbers. The new numbers that have been calculated are as follows. 6.7969. 5, but again, we're only keeping 3 significant figures, and this would round to 6.80 grams to wrap up this problem on the enthalpy. The next question we had was about using the given mass and a chemical formula in order to determine the number of moles. This problem can be broken down into a few steps. The first one is to calculate the molecular weight of the compound, and in this case we've got iron 3 sulfite. And to do that requires a few steps. Once we have the molecular weight, then we can convert grams to moles using the molecular weight, and in this case we'll need to divide. So up top, to calculate the molecular weight of iron 3 sulfite, we're going to need to add together a bunch of different things. The way that I personally think about breaking up this problem is by the irons. I've got 2 of those, and then I've got 3 times sulfite. So for me, I would calculate this mass on its own and then multiply it by 3 and then add it to twice the iron mass. So this is how I think about this particular molecular weight. The same would apply for the compound in the text, the chat as well, calcium phosphate. You could apply the same technique there. So in this case, we're going to have 1 times the sulfur plus 3 times the oxygen. And that's going to be, I don't know, 80 or so. Let's get sulfur in here. 32.065 plus 3 times the oxygen value, 80.0632 grams per mole. All right, then we're going to multiply that by 3. So let's get a value for that, 240 and change, yeah? And we need the mass of iron in this case, 55.845 grams per mole. I boxed myself in here. Let's get a number for that now. I get 351.8796. If we're really being careful about sig figs, then the 3rd decimal place would be where I would round. So this would become 880. grams per mole. Woo! We've got our first ingredient, the molecular weight. Now that we know the molecular weight, we can go back and convert our given amount of grams. 8.2 grams of our iron 3 sulfite. And now we're going to be dividing by the molar mass, 351.880 grams. And we've got 1 mole up top. So let's get a value. Should be fairly small. And we would only be able to keep 2 sig figs in the end of this process based on the information given. I get 2.3 times 10 to the minus 2 moles. Sounds like we got the same thing. I'm going to stop recording.